Hello and welcome to podcast.init, the podcast about Python and the people who make it great. When you're ready to launch your next app or want to try a project you hear about on the show, you'll need somewhere to deploy it, so take a look at our friends over at Linode. With the launch of their managed Kubernetes platform, it's easy to get started with the next generation of deployment and scaling, powered by the battle-tested Linode platform, including simple pricing, node balancers, 40 gigabit networking, dedicated CPU and GPU instances, and worldwide data centers. Go to pythonpodcast.com/linode, that's Linode, today and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host, as usual, is Tobias Macey, and today I'm interviewing Eugenio Angriman about NetworKit, an open-source toolkit for large-scale network analysis. So, Eugenio, can you start by introducing yourself?
Yeah, thank you, Tobias, for the introduction. My name is Eugenio Angriman, and I am a PhD student at Humboldt University of Berlin. I work with NetworKit almost on a daily basis in my work, and I'm happy to be here talking about it with you.
And do you remember how you first got introduced to Python?
Yeah, so I was introduced to Python quite late, I have to say, when I was working on my master's thesis. So my thesis was mainly about efficient graph algorithms, and I was quite familiar with the graph algorithms, but not so much with programming. So I decided to implement my algorithms in pure Python because I wanted to learn this new exciting programming language. But unfortunately, as you know, when it comes to performance, Python is not as good as C++, especially when you want to go to large networks. So I kept using Python, but I started using the GraphTool library, which is much more efficient because it implements algorithms in C++ and it exposes them to Python. And since then, I still use Python to do data analysis or to do plots or to write utility tools for that I use on a daily basis. So I'm super happy with Python.
And you mentioned that you had used GraphTool as you were starting to get introduced to Python, and that's a project that I had on the show recently. But I'm wondering how you ended up moving from GraphTool to NetworKit and how you ended up getting involved in the NetworKit project and sort of what your comparison or what your motivations are for using NetworKit instead of GraphTool.
So when I started my PhD, in a group that was developing NetworKit at the moment. So I started using NetworKit for that main reason. And all the people I was working with were experienced with NetworKit, so they could introduce me better to the environment and how to properly contribute to this project.
And so can you dig a bit more into the network project itself and some of the story behind sort of how it got started and some of the core focus of the project?
So as far as I know, the NetworKit project started in 2013. So 8 years ago, as we speak. Now, unfortunately, I don't know so much about NetworKit's early years because I started contributing to this project since 2017. Anyway, as far as I know, one of the main driving forces of NetworKit was Christian Stout, which was at the time one of the first PhD students of my supervisor. So he was working on graph algorithms. He preferred starting writing his own library rather than using something that was already there available. Since then, I have to say that NetworKit kept growing, not only thanks to the early efforts of the founders, but also thanks to the help from external contributors like students, researchers, and other people from other universities. So look in our website, we have a long list of collaborators, and we also can check that in our GitHub page. Without their help, NetworKit would have far less features than the one that it has right now. For example, we had many students that work with NetworKit for their master thesis or bachelor thesis. And once thesis was finished, we included their algorithms inside the NetworKit. And so they were available to use for the open source community. Some other code was developed by PhD students or other postdoc researchers as part of their research. Once a paper is published or some work is accepted for publication, then we integrate the code or the new algorithm presented into NetworKit, so it is available for everyone to use to reproduce our results. So maybe a long story short, the NetworKit was and still is a really collaborative effort that involves many people around the world and to provide the efficient, scalable algorithms for large-scale network analysis.
And with that emphasis on efficiency and large networks, I'm wondering what are some of the situations where you might encounter data sets of that particular scale? Because I noticed on the website it says that it's able to process on the order of billions of nodes in a graph. And just wondering what are some of the sources of those types of data and some of the acute challenges that you come up against as you're trying to manage efficient processing of those data sets?
So as you can imagine, many of today's phenomena or problems can be represented as graphs. And depending on the problem or how you're trying to modeling it, then you might end up with graph with different types or sizes. Maybe I can start with the most obvious example, which are social networks. So we all know that social media is used by every day by a lot of people, and it involves billions of people around the world. So just representing interactions between people leads to graphs that are huge in their size. And we might also add more about users. We might also add places, events, or pages, and many other things that make these networks even bigger. Maybe another simple example are road networks. So one can see a road as an edge and crossings as nodes. Road networks alone can also build up very large graphs. So if you just think about road networks in the US or in Europe, we can have graphs with millions to hundreds of millions of nodes. And third obvious example, of course, is the internet. So the internet can be represented as a graphs with nodes as web pages and edges as hyperlinks between pages, and representing portions of the internet. We might end up with the network with a considerable size. So these are three obvious examples, but we can go on more with the other examples. I guess that with the interest of time, we can move on to other questions.
Yeah, there are definitely a lot of opportunities for building up networked structures. And your point of the internet as well, there's web pages with links. There's also machines with network connections, and just even just managing to map out the sort of core backbone of the internet with ISPs and edge providers and things like that. There's all kinds of interesting analysis to do there. And then in terms of the sort of overall ecosystem of managing network analysis, particularly in Python, as we mentioned already, there's the GraphTool project, another one that is pretty well known as NetworkX, which I know is implemented in pure Python, so it has some issues in terms of its scalability. But how would you sort of characterize NetworkIt's position in the overall ecosystem of Python and doing network analysis, particularly on these larger data sets?
Yeah, so I think it's a really interesting question, and I think that the answer also why NetworkIt was born. So I think that this ecosystem of Python libraries for network analysis has two main types of libraries. So as you mentioned about NetworkX, we have libraries that are implemented in pure Python, which is a really popular language, so they can count on many contributors who provide a wide range of features, right? On the other side, we have libraries like a GraphTool, which I also used in my master's thesis, that implement their algorithms efficiently using C++ and expose them to Python. So they have maybe more restricted set of features than other libraries like NetworkX, but they provide them in a more efficient way. So with NetworkIt, we are trying to fill this gap. So we want to provide a wide range of features with the new algorithms and state-of-the-art features for network analysis without sacrificing performance. So we want to provide many features, but efficiently to the users in the Python community.
We can dig into it a little bit later, but one of the interesting things to touch on is who the primary audience is for NetworkIt, whether it's built for the purpose of researchers and being able to do research and analysis of networks, or if it's intended for sort of more broadly use by developers who might encounter some of these networked data sets and need to incorporate graph analysis as part of a larger application, and just how that informs the interface for the library and the features that you focus on building out.
Yeah, I think that NetworkIt can serve successfully both of these kind of audiences. So we were an inexperienced researcher, maybe a researcher that doesn't have a lot of experience with coding or computer science can still use NetworkIt thanks to the handy Python interface, because it's really straightforward to use. So it's one of our targets. Another target, of course, other more experienced developers who want to develop efficient algorithms for network analysis. as we also provide NetworKit as a C++ only library. So if one also wants to work just with C++, then it is also free to do so by developing algorithms directly using C++ and the NetworKit APIs. So we are targeting maybe also a broad range of users, not just a particular one.
In terms of the actual analysis of the graphs, I'm wondering what are the algorithmic challenges that you run into and some of the issues with complexity analysis of the data that you're working with and how to properly traverse and analyze it?
In my experience, I faced quite a few of these challenges. So one is, for example, when you aim for scalability and high performance, then you cannot afford an algorithm that has an empirical running time complexity that is super linear. So this, as we all know, maybe just does not scale. So I say empirical and not worst case run time complexity because many scalable algorithms that we develop also in NetworKit have indeed a worst case time complexity that is super linear like quadratic. But in reality, so in real world graphs, they are much faster. So this is one aspect about maybe runtime complexity. Other challenges, in my opinion, concern the memory. So one simply cannot afford to use too much memory. So for algorithms that target large graphs, similarly with time, we cannot store more than a linear amount of additional memory. More of that does not simply scale. And another aspect that I think is very important is the cache locality. So many graph algorithms, for example, need to traverse the graph, which means that they access the graph data structure in a kind of unpredictable way. And this often leads to cache misses or inefficient memory accesses, and this leads to performance loss. So we experienced this phenomenon in some of our recent papers. A considerable amount of time of our algorithms was spent just waiting data to be loaded than just processing the data. So even if we used a faster CPU, then this would not speed our algorithms up. So the main bottleneck was really the memory bandwidth. This is a huge issue, it's also documented in the literature, I noticed, and it can probably be mitigated with using a better graph data structure or by using some dedicated hardware to speed up the algorithms.
Yeah, and the structures themselves is another thing worth digging into. I'm wondering sort of what the representations are of these graphs and some of the considerations and trade-offs that go into the actual storage of the data that you're analyzing, and sort of things like the types of attributes that are available on the different nodes and the edges, or if the edges don't have any information associated with them other than the nodes that they're connecting, and just there are a number of different ways that you can approach building out the actual graph structure and where you put the relevant information.
Yeah, true. So at the moment, NetworKit uses adjacency list structure. So basically a vector of vectors, which is a really simple way to store a graph in memory. But maybe it's not the most efficient way to do that. So we are working into improving this. Concerning attributes, at the moment, NetworKit does not provide this feature. So it does not provide a way to express additional attributes for nodes or edges. The only additional thing one can store on edges are simply edge weights, so just a floating point number, which of course is something that lacks compared to other libraries. We are working also on that as an additional feature in NetworKit for the future.
In terms of the actual NetworKit project itself, can you dig into how it's architected and some of the design principles that you're focusing on for how to build out the library and make it maintainable and make it accessible for other people to contribute to?
So the NetworKit, at least the NetworKit Python package, is organized in different modules. These modules are independent. Each module basically tries to solve a specific problem or a family of problems. So for example, obvious problem when working with graphs is reading and writing graphs. So we have the graph.io module that does only that. So reads and writes graphs according to a specific format. Other modules are, for example, the community module, which implements all the algorithms about community detection and so on. So then, similarly to Graph2, I think NetworKit is built on top of a C++ core library, and they communicate together using a Cython.
As you mentioned, NetworKit has been around since 2013, and you've been working on it for about 4 years now. And so over that time, I'm sure that there's a certain level of maturity that it's reached. And after a while, software projects start to go through a phase where the adaptability or its capacity to change directions or morph starts to kind of solidify. And so there's a more concrete structure around it. You're still able to iterate and add new features, but the sort of overall design has become sort of what it's going to be. And I'm wondering how that factors into how you manage quality and onboard new contributors to the project.
Yeah, as many other open source projects, in order to ensure a minimum of code quality and maintainability over years, we require that every new NetworKit algorithm that comes from external developers, but also from us, so internal developers, must be tested. So all algorithms must be tested in test suite. Now then, tests are executed in our continuous integration system, which checks that the code works on all platforms, so all major platforms like macOS, Linux, and Windows. On top of that, we also add static code analysis with code linkers, and we treat nearly all warnings as errors. So this helps us spotting common coding mistakes without having to look into them ourselves. Then once all this CI pipeline works correctly, then we have introduced recently a mandatory review process where at least one of the NetworKit maintainers must approve changes before the changes are actually merged into NetworKit. This, of course, makes adding new code into NetworKit harder and takes more time, but I have to admit that over time it improved a lot the quality of the code base, and I wouldn't go back.
In terms of the actual research that is being done with NetworKit and just the overall space of graph structures and networked data, what are some of the active areas of research that are ongoing and some of the specific areas that you're focused on during your PhD?
So I think that there are quite a lot of research areas concerning network analysis. Maybe I can start with one that I'm most familiar with, which is centrality. So as some of you might already know, so given a graph, one might want to find which are the most important nodes or edges according to some specific criteria. Now, centrality basically assigns a score of importance to each vertex or edge in the graph, so one can easily determine which are the nodes or the edges that are the most important in the graph, so the ones that have the highest centrality score. Now, unfortunately, computing these centrality measures is very expensive. They were really not conceived with scalability in mind when they were first introduced many decades ago. So today is challenging to efficiently computing those centrality measures in large-scale graphs. Now, the research in this area started to take different directions to solve this problem. One way is to simply approximate the centrality score instead of computing them exactly. And this allows us already to speed up this process quite a lot. Another solution is just trying to find the top K most central nodes. Usually this has been shown to be much faster than just trying to compute the centrality scores for all the nodes. And another issue about this problem is graphs today change. So new friendships are established in social networks, roads are destroyed and built continuously, so graphs are not static in most scenarios. So another challenge here is to update those centrality scores after the graph changed. And this usually can be done much more efficiently when starting from an initial state when centralities are already known, or instead of doing all the computation from scratch after the graph changed. All right, then another research area that people are really exciting these days, I think, is node embeddings. So this is not really surprising, I think, because node embeddings basically are a bridge between graph theory and machine learning. So in machine learning, people often work with datasets where each element is basically represented as a vector of values, and these values are later processed by a machine learning model. Now, representing graphs or nodes as vectors is not trivial. Node embeddings basically simply achieve this goal. So they are used to create vectors or a vector representation of a node. That can just use to create a vector representation of a node that can be used later in tasks like node classification.
Those are definitely interesting areas to dig into. And I know that in particular, machine learning on graph structures is an area that's gaining a lot of attention currently. But your point too about the evolvability of graphs where you're not just working with a static data set is an interesting point as well. And I'm wondering what the, I guess, challenges are in terms of being able to diff the state of a graph where you have a snapshot of the graph that you're doing the computation on, and then being able to understand what are the changes to this graph from time A to time B, and then being able to iterate through that graph and just being able to manage the diffing of those states, because as a graph evolves, it's not going to be, the same as if you're diffing a text file where somebody appends lines, because new nodes might come in which have edges that, feed into nodes that you've already computed. And I'm wondering just how you manage those differential states.
Yeah, there are lots of techniques that you can use to manage these changes. So, common way to deal with these changes, for example, finding which nodes are affected by the change. So when I add a new connection or a new edge, maybe new shortest paths might be created thanks to this new edge. So this new edge might change the score of some of my nodes in the graph. So a good starting point here is to understand which nodes are affected by this change, and then try to reduce the computation by just focusing on those affected nodes and not processing all the other nodes that are not affected. This was already shown to be an effective way of dealing with this kind of dynamism in networks.
And then another interesting element of dealing with graphs, particularly as they scale, is being able to effectively parallelize the computations and understanding where to shard the graph structure if you need to scale out across multiple machines. And I'm wondering, what are some of the interesting challenges that you've run up against with that, or if you have kind of punted on that problem with NetworKit and just say we deal with structures that can fit in a single machine, or if there are any aspects of that sort of graph partitioning that you need to deal with in sort of parallelizing the algorithms?
I didn't deal with this kind of huge graphs that you have to share into different machines. So I only worked with the shared memory algorithms, where the graph can fit into one single machine. However, I also worked with the distributed memory, but in a different kind of scenario. So we used multiple compute nodes, and each compute node hosts a copy of the graph. So in this way, when we have to distribute the computation on a single graph, we can not only use parallelism on a single machine to distribute the work over multiple threads, but we can also distribute the work on multiple compute nodes that basically do the same thing on the same graph. And then at the end, we gather the results from all these compute nodes and combine them together to get the result faster than working just on a single machine. And this also had worked quite well in our case, but this again requires the possibility of storing the graph on a single machine.
In terms of being able to use NetworKit and do some of these network analysis tasks, I'm wondering how much overall background knowledge is necessary in terms of graph theory and graph algorithms versus somebody who just wants to pull in NetworKit and be able to say, I want to compute the node centrality score for this node given this graph for purposes of building a web app or something.
Yeah, I think this depends on what one wants to achieve. So if one can want just to use some basic network functions, then I think that just a basic knowledge of Python and of graph theory, like just what is a graph and how distances are computed in graphs, is already more than enough to start working with NetworKit. So NetworKit algorithms are really straightforward to use. In a few lines of code, you can read a graph, launch some algorithms, and visualize some results. So I think that rather to use NetworKit, one needs to have a background about network analysis in order to understand which kind of algorithm you want to use to solve your problem and to interpret the results that are yielded by NetworKit algorithms.
And then in terms of the capabilities of the project, I'm wondering if there are any aspects of the library or its feature set that you think are underutilized or often overlooked, and just things that you think should be highlighted and mentioned for people who are starting to look at NetworKit or starting to think about ways that they can use graph structures to solve interesting problems?
So I think that one aspect I think is still underutilized because it is very recent is our new NetworKit in the cloud system. So we presented this new system at the SIAM conference on computational science and engineering in March of this year. And basically we are offering now the possibility of using NetworKit inside a Jupyter Lab instance with just your web browser. So basically you can use NetworKit just using your web browser without needing to install NetworKit in your machine, because the computation is totally done in the cloud. So yeah, of course, the cloud resources are limited, so you cannot run expensive algorithms on large graphs, but at least this offers you the possibility of trying NetworKit without installing it on your machine.
In terms of projects that you've seen built with NetworKit or ways that you've used it in your own research, what are some of the most interesting or innovative or unexpected ways that you've seen it employed?
I really have to thank you for this question, because when I was preparing for today's episode, I did some research on Google Scholar, and I was quite pleased in finding that there are quite a lot of papers out there from other research areas that are using NetworKit in their experimental pipeline. So maybe I can try to mention a couple of them. One is from Jochen Keutel. He's from the Voith University of Applied Science in Berlin, and he joined the NetworKit Day last year, and this is an event that we organize on a regular basis to get in touch with the NetworKit community, and he presented a paper about bibliographical networks. So he gathered datasets from various universities in Berlin, and they were about German fictional literature or international scientific bibliographies and other biographical data about the authors. And he created some networks that were connecting the authors with their writings and also about other people involved in their writings and other institutions. So he created some big graphs and used NetworKit to find more insights about the historical evolution of some discipline, or which were the main characters or agents that developed some field in the literature, or which were the institutions responsible for the development or the relevance of some field. So it was a really interesting talk from him. And on our NetworKit website, we also have a page dedicated to NetworKit Day, and one can also download his slides from there. Yeah, this was a really interesting project, I have to say. And the second example that I found on Google Scholar is a paper that is titled Cloud Impact Assessment on Road Networks and Healthcare Access at Jakarta, Indonesia. So, as some of us already know quite well, I guess, so Jakarta is a huge coastal city, which unfortunately is sinking underwater, like Venice. And here the authors are trying to study the impact of floods in Jakarta, and they're using data from OpenStreetMap, so basically the Jakarta road network, and they also use NetworKit to analyze the road network before and after a flood. So in particular, they study the reachability between citizens and the healthcare facilities. Yeah, they use centrality measures such as betweenness to determine the importance of some roads before and after the flood. And this is quite useful, they showed, to predict congestions in road and see how the flood impacts basically the possibility of citizens to reach healthcare facilities.
And then as far as your own experience of working on NetworKit and using it for your own research, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
There are quite a few lessons that I learned in this process. So one of them, I think, is think before coding. The first solution that pops up in your mind might not be the best one or the right one for the problem that you are trying to solve. So I think it might be very tempting to start coding immediately without thinking enough. This often results in losing time because you have to fix the code later if you didn't implement the right algorithm or not implement it in the right way. Another cost, I think, of wrong decisions is that if your code ends up in production, then some users might rely on some functionality or some API that you later want to remove or change. And you have to take this into account. So you cannot take arbitrary decisions later. So removing functionalities or changing APIs, because this might break other people's pipeline. So it's really important to think thoroughly before introducing some important change or new algorithms, because it might be quite hard to undo these actions. I think that another lesson that I learned that applies for lots of people is not being intimidated by criticisms from other developers. So many developers might raise criticism to your code, especially during a code review. I have to admit that some of my contributions to NetworKit were not so brilliant. Other more experienced developers bluntly say, why are you doing this? This is really bad for this or that reason. And immediately I felt like, oh no, now my incompetence is shown to the entire world, and I'm really ashamed of that. So, but I think that these criticisms are really, really useful because, they teach me quite a lot. So I learned quite a lot from them. Now I'm really, really thankful to those people who spend time in criticizing my code, because they taught me a lot of useful lessons for the future.
Yeah, code review is always a scary time, and there are definitely a lot of issues around things like imposter syndrome and the question of trying to remove your ego from your code, and sort of like your code is not you, but it's a complicated issue, particularly for people who are first getting involved in open source. And then in terms of, if somebody is looking to do some network analysis and they're figuring out which library to build on top of, what are the cases where NetworKit might be the wrong choice for doing some sort of network analysis or graph structure discovery?
Yeah, so I can think at least about two scenarios where NetworKit is not the right choice. One is, as we were saying before, when you are dealing with graphs that are so big that they cannot fit on a single machine and you need distributed system. So as I said, NetworKit is a shared memory library, so we do not support distributed memory, and you want to go for other kinds of library if you are dealing with these kind of graphs. And another scenario that I think is when you want efficient algorithms that are tailored to GPUs. So for example, algebraic algorithms. So algebraic algorithms often rely on operations with matrices and vectors, which can often run much more efficiently on a GPU rather than on a CPU. So far, NetworKit does not exploit GPUs. So in that case, I would suggest to go to other libraries such as Gunrock or Hornet, because they really take advantage of the resources provided by GPUs.
As you continue to build out NetworKit and as you're working to finish out your PhD, what are your plans for the near to medium future of NetworKit, or just some of the overall roadmap of the project?
Yeah, so the wish list is quite long, but unfortunately resources are quite limited. So right now, as I said, we are working on a new and more efficient graph data structure. Yeah, right now the graphs are stored as these adjacency lists, which, we know they pose some limitations in terms of memory. This is one direction we are trying to take. Another one is to add support for node edge attributes. So one can store inside the NetworKit graph additional attributes instead of being forced of storing them elsewhere. Another feature we are working on is building a new benchmark framework for NetworKit. So specifically, we want to answer the question, what happens if I apply this change? Which algorithm becomes faster or slower? So right now, we have to do this manually. We have to set up some small experimental pipeline, measure how fast an algorithm become after a specific change, and this is not really scalable. So we want to automate all this process and measure how performance change if we do a specific change in the code base.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And so with that, I'll move us into the picks. This week, I'm going to choose the author Edgar Allan Poe to feed off of my pick last week of H.P. Lovecraft. So if you're looking for an interesting read or some short stories, Edgar Allan Poe has always got some interesting stuff. So definitely worth checking out if you haven't ever read anything by him. So with that, I'll pass it to you, Eugenio. Do you have any picks this week?
Yes, I have. So yeah, during the recent lockdown months, I have to say that books have been a great company to me. And in particular, one of the books that really helped me in coping with this sort of forced solitude was the Spinoza problem. So this book was written by Irving David Yalom. So, and due to these ideas, I really have to cut this. So due to his ideas, Spinoza was forced to leave his Jewish community in Amsterdam and develop his new ideas alone. Yeah, his life and his revolutionary ideas written up as a novel were very inspiring to me. So that's a book that I strongly recommend.
I'll definitely have to take a look at that. Well, thank you very much for taking the time today to join me and share the work that you're doing on NetworKit. It's definitely a very interesting library and interesting problem domain, so I appreciate the time and energy you're putting into that. Best of luck on your PhD, and I hope you enjoy the rest of your day.
Yeah, thank you too.
Thank you for listening. Don't forget to check out our other show, the Data Engineering Podcast, at dataengineeringpodcast.com for the latest on modern data management. And visit the site at pythonpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts@podcastinit.com with your story. To help other people find the show, please leave a review on iTunes and tell your friends and coworkers.